Hello everyone, and welcome to the third and last session of our three-part Applied Remote Sensing training, SAR for detecting and monitoring floods, sea ice, and subsidence from groundwater extraction. My name is Erika Podest, and I'm a research scientist at NASA's Jet Propulsion Laboratory, as well as an instructor with the ARSET program. I will be hosting today's training. Today, I will be joined by guest lecturer Dr. Franz Meyer, who is professor for radar remote sensing at University of Alaska Fairbanks, as well as chief scientist of NASA's Alaska Satellite Facility Distributed Active Archive Center. Today, he will be focusing on detecting and monitoring floods with SAR. To begin, I'll provide an overview of our training before we begin this session. I'll first be providing an overview of our training before we begin this session. The objective of this webinar series is for participants to learn how to use SAR to detect and address potential disasters related to sea ice, floods, and groundwater extraction. And these sorts of events can have a large impact on human lives, infrastructure, and the economy. So SAR can be critical in informing on-the-ground efforts on disaster mitigation efforts and resilience. By the end of this webinar series, participants will be able to detect and monitor sea ice to identify potential risks to shipping and coastal erosion. So that was the first session. Generate subsidence maps due to groundwater extraction to inform risk and resource management. That was the second session. And then detect and monitor floods in order to more closely monitor increase or decrease of floodwaters and better inform disaster response and management. And that is today's training. Here's an outline of the training. Today is the third and last session of this three-part webinar series. All presentation slides, recordings, and Q&A transcripts will be available on the training page. There will be one homework assignment, which will open today, Wednesday, November 1st, and it will remain open until November 17. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. And finally, before we get started, I just wanted to remind everyone that if you have a question, to please type it in the questions box. And under this platform, it is located in a different place. It's at the bottom right under the 3 points. There's a drop-down menu. And one of those three options in the drop-down menu is questions. So please write your questions there, and we will address all questions at the end of the webinar. And feel free to type in your questions as we go along. All the questions will be assembled into a Google Doc, and that Google Doc will then be posted onto the training page with all the answers. We're very pleased to have Dr. Franz Meyer as guest lecturer today. He is an expert in SAR and has been a major force in global SAR capacity building efforts and in making SAR more usable by the scientific and applications community. There's a reason he's known as the SAR evangelist. Thank you, Dr. Meyer, for joining us today and for so generously sharing your knowledge and wide experience in the use of SAR for detecting and monitoring floods. Welcome.
Thank you, Erika, for the kind introduction. So my name is Franz Meyer. I'm a professor at the University of Alaska Fairbanks, where I'm specializing on teaching topics of microwave remote sensing. I also am the chief scientist of the Alaska Satellite Facility, which is probably one of the data sources that you will be using when you're working with synthetic aperture radar datasets. So I'm giving you today session 3 of this 3-session training on SAR for detecting and monitoring floods, sea ice, and subsidence. And so my session today will focus on the monitoring of flooding events with SAR. The content today is intended to introduce you to the properties and the benefits of synthetic aperture radar datasets for flood monitoring, but specifically for benefits of some of the more commonly used datasets these days, which is Sentinel-1, an ongoing mission launched by the European Space Agency that's currently in orbit and provides regular observations for flooding events, in an upcoming mission called NISAR that I'll introduce. That's a collaboration between NASA and the Indian Space Research Organization, and will also provide fantastically useful data sets for flood mapping. I hope that you walk away understanding how different land cover types look in SAR images and how specifically water surfaces look different from most of the other land surfaces, and therefore can be distinguished from these other land surface types. We will talk about how to identify open water areas using thresholding approaches, and I will show you a notebook, a Jupyter Notebook, that you can use to exercise thresholds-based flood mapping for a sample data set over the Hindu Kush Himalaya. And at the end, we'll talk about the capabilities of these threshold-based algorithms, but we also talk about some of the limitations of these techniques that will help you use the right data set for your particular flood application. So I believe that right now you are taking this course at the perfect time. It's a really good time to learn about SAR right now, and it's specifically because of two fantastically useful sensors, synthetic aperture radar data sensors, Sentinel-1 and NISAR. So I want to talk to you about their sensor characteristics and how you can access data sets from these two missions, which both are very useful for the application of flood monitoring. So SAR has undergone a great transformation over the last maybe 5 to 7 years, and it is related to the advent of new sensors that provide free and open, regularly sampled data sets on a global scale. You see here an example in this animation that shows you repeated images over Bangladesh. In these images, you see a variety of different brightness patches, and you see that at some point, very dark patches show up. These are surface water extent features we'll talk about in this class, while these surface water extent features look very dark in SAR images. But the key is that these modern data sets, such as Sentinel-1, the upcoming NISAR mission, and other many upcoming missions in the space of SAR, they provide you regular observations every 6 to 12 days over these features that are flooding in the landscape, and the regular observations in the free and open data set are really key to use SAR data sets in operational response and operational flood monitoring. So I want to bring those sensors to you real quick. The first of those sensors you probably already have heard of, and maybe you have used that sensor already in your work. It is Sentinel-1. Sentinel-1 was launched in 2014. It's a constellation of 2 C-band radar satellites. We'll talk about the different wavelengths and bands of SAR here in a little bit. Sentinel-1 was brought along a pivotal change in the use of SAR, because it was the first SAR satellite system with an operational mission. This means that Sentinel-1 is required to observe every point on Earth at a 12-day cadence. Some places in Europe at an even higher cadence, usually 6-day cadence. So we have regularly, reliably observed data sets. Because it's a synthetic aperture radar, one of the benefits of it is cloud-free and weather-independent, and it images all land masses, all coastal zones, and shipping routes every 6 to 12 days. Additionally, Sentinel-1 is also specifically designed for INSAR. While this particular lecture does not utilize the capability of interferometric SAR, you heard about INSAR in previous lectures, especially the ones that focused on landslide displacement from landslides. And key to Sentinel-1 is that all data sets they observe are freely and openly available. This free and open means that you can access the data sets for free, independent of your application. So you can apply these data sets to any kind of application you want. So Sentinel-1 was launched by the European Space Agency, as mentioned earlier, in 2014. Starting in 2014, free and open data sets globally acquired. It's a constellation of 2 C-band SAR sensors. You can try to remember already. C-band is a microwave wavelength that is used fairly heavily in Earth observation, and it has a wavelength of about 5.6 centimeters. Sentinel-1 is also providing multiple polarizations, typically dual pole data in VVVH polarization over land. Also, polarization is something we will talk about more later in this class. The data sets have a resolution of roughly about 10 meters, so 5 by 20 meters, roughly about 10 meter scale pixel size. And every image has a swath of 250 kilometers. So you get very large coverage with every rotation of the satellite around Earth. The temporal samplings is 6 days over Europe and 12 days for the rest of the globe. And it has both imaging and interferometry capability, as mentioned earlier. And one of the things you can do is the image that you see in the background here is actually a flood detection image. The different shades of blue here show water extent at different time steps, and how Sentinel-1 can be useful for flood mapping we will discuss in this class. This animation shows you how the constellation of Sentinel-1 sensors operates to ensure global coverage every 12 days. So we have 2 satellites that are offset by about half an orbit, scanning the planet completely within 12 days. Unfortunately, one of these 2 satellites in this constellation, specifically Sentinel-1B, so the 2 constellation satellites are called Sentinel-1A, which was the one launched in 2014, and Sentinel-1B for the second satellite launched in 2015. Sentinel-1B had a failure in December 2021 and is currently not providing any additional data sets. So there's some limitation in coverage at the current point. However, a replacement satellite called Sentinel-1C is planned to be launched sometime in 2024, likely late 2024 or early 2025. If in the full constellation of 2 satellites, Sentinel-1 provided global observation with quite high density, this plot shows you how many acquisitions were made per month in 2021 when the full 2 satellite constellation was still available. So you see that there's lots of coverage, especially in the higher latitudes, in many of the tectonic sites, and also good coverage for the rest of the land masses. So all the blue areas shown here, these are the land masses covered by Sentinel-1. After the failure of Sentinel-1B, the coverage decreased to some degree. So this is giving you a little bit of an idea, this animation, what the coverage looks like since then. So there are some areas that have not been covered extensively, such as Siberia and some places in Africa. Over time, ESA started adjusting a little bit the acquisition scenario to have more global coverage available, even with only 1 satellite in place. But notes that in 2024, late 2024, we expect that Sentinel-1C will be launched to recover the full capability of the Sentinel-1 constellation. So Sentinel-1 is one of those 2 data sets that you will work with extensively, I would expect, when using SAR for flood monitoring. Another data set along the similar properties is the NASA ISRO SAR, or short NISAR mission. So this is a collaboration between the US space organization NASA and the Indian Space Research Organization ISRO. They collaborated to build this mission, which an artist view you see on this slide. NISAR is going to be exciting. It's launching in spring of 2024. We expect the launch to happen probably around April next year. It brings a few firsts. It's going to be the first spaceborne L and S band dual frequency radar satellite. It will also, like Sentinel-1, provide full global coverage every 12 days. But in contrast to Sentinel-1, which operated at C-band, remember C-band was about 5.6 centimeters wavelength, NISAR will operate at L-band, which provides at roughly 25 centimeters wavelength. So it's about 5 times the wavelength. And the longer wavelengths has some benefits for a number of applications, including flood monitoring. We'll discuss these benefits a little bit later in this lecture. NISAR will provide an enormous amount of data set or data volume. Per year, NISAR is expected to provide 50 petabytes of data, which roughly is about maybe 10 times as much as Sentinel-1. Over its planned mission lifetime, which is 3 years, we have 150 petabytes of data that NISAR will bring. All data from NISAR are also free and open. So again, you can access these data sets for free, and you can apply these data sets to any application that you care about. Specifically, NISAR will provide data that feeds into a number of science applications disciplines. The main science disciplines supported by NISAR include solid earth science. This includes things like studying earthquake dynamics, volcanic cycles, landslides, ground subsidence from groundwater extraction, and so on. It additionally supports cryospheric science. This includes the movement of glaciers, the movement of and extent of sea ice, and the movement and extent of ice sheets. And then lastly, the L-band data set is very useful for ecosystem science. So it's going to provide data sets that can be used to understand forest biomass and biomass change, agriculture extent and agriculture dynamics, as well as wetland. It also will support wetland monitoring. In addition to these science disciplines, there are a number of application disciplines, such as flood monitoring, that will be supported by NISAR quite well. So both of these data sets, Sentinel-1 and NISAR, will be available for you, for your research through the services of the NASA Alaska Satellite Facility, or the NASA ASF DAC. DAC stands for Distributed Active Archive Center. So NASA operates many of these data centers for different disciplines, and these data centers house all the NASA-owned and NASA-related Earth observation data sets for you. ASF is the data center for synthetic aperture radar data. It was established in 1991. We were established back in the days mostly to provide downlink from a downlink station from Earth observation satellites. But this mission was expanded a few years later to also include the data archive. Today, ASF is providing access to about 20 petabytes of SAR data through its archive. And ASF is unique in the fact that all of our data are located in the Amazon Web Services cloud, and all data are ready for you to use. So none of the data need to be ordered. They are all on live spinning disks, ready for your science usage. ASF provides access to more than 45 years of data sets these days, starting in 1978 with the CSAT mission. It is the current, one of the current archives, global archives for Sentinel-1, shown here on the left-hand side, and will be the data center for NISAR. So all the level 0 to level 2 data sets from NISAR will be available through ASF. As a side note, some of you may be aware of another NASA project that's called OPERA. OPERA provides large-scale level 3 science products from Sentinel-1 and NISAR. OPERA is producing things like surface water extent, so they provide a product that we'll talk about today a lot. They also provide global surface disturbance information, as well as North America-wide ground displacement. These data sets from OPERA will also be available through ASF. Specifically, the displacement data set will be available through ASF. I'm not going to give you a grand tour of ASF in this particular lecture, but the slide decks contain some links. On this slide here, you see a link to the ASF search interface. This is a one-stop shop for the discovery and the on-demand processing and downloading of SAR datasets from missions such as Sentinel-1 and NISAR. So all of your Sentinel-1 and NISAR datasets you'll be able to find through this convenient search and discovery interface. I also provided a link to the ASF website. This gives you more information about the sensors we hold and all the other activities that ASF is conducting in the field of synthetic aperture radar. So please check out these links. And there's also feedback buttons on this website, which you can use to ask ASF any questions you may have. Now, both of these data sets are great for surface water mapping. And in this next section, I want to talk about why SAR is really good for detecting surface water in a landscape. So firstly, SAR is really useful for emergency response for some simple reasons. SAR datasets operate in the so-called microwave spectrum, or the radar spectrum of the electromagnetic, overall the electromagnetic spectrum. Let me turn on my laser pointer here. So we're operating in this frequency range between about 1 centimeter wavelength and roughly about a meter wavelength. This is where all the microwave datasets sit. This is distinctly different from the visual range, which is in the order of a few microns or a few hundred nanometers. One of the differences between those two spectra is that the atmosphere is very transparent in the microwave window, which allows weather-independent observations of planet Earth. So for flooding, that's particularly important. Flooding often happens during cloudy conditions when rainfall is happening, and having a weather-independent and cloud-penetrating observation platform for observing the impacts of severe weather is very useful, and radar provides that capability. Other benefits we'll talk about is that SAR is really good for change detection. This is related to the fact that SAR, or radar, is an active observing instrument. So we are actively sending out microwave signals from a satellite. Those signals travel to the ground, get reflected, and come back to our sensor. This makes us independent of sunlight, and it provides a very stable observation scenario. So if you take an acquisition today, and we take a repeated acquisition 12 days later, because we are sending the exact same amount of energy from the exact same location down to Earth, we have a very repeatable observation condition, which lends itself really well for change detection. Another reason why SAR is really useful is because the observation wavelength is quite different from what you're used to from optical systems, or from what you're used to, what you're seeing with your eyes. This may make SAR datasets a little bit difficult to interpret at first, but it means that you provide complementary data to optical sensors. So we are providing independent information about the surface. We are seeing different things about the plants and the surface structures on a landscape. And so that's really useful. Combining optical data with SAR datasets together in classifications or interpretations can be quite useful. This animation here, developed by the German Aerospace Center, gives you a little bit of an idea of the benefit of the weather independence of these SAR datasets, and why it is particularly important for understanding hazards related to flooding events. So the idea, as mentioned earlier, is during flooding events, usually we have poor weather conditions, we have cloud cover and rainfall, and optical datasets won't be able to see the ground from space. Ground will be obstructed by clouds. SAR satellites such as TerraSAR, Sentinel-1, NISAR, however, have the capability to penetrate through these clouds. You can see that here in a second in this animation. So we can see through this cloud cover. This is the first benefit for flood monitoring. But then when we hit water surfaces, we also see that these water surfaces look quite different than the landscape. You see water is very dark in these images, much darker than the rest of the landscape. And we will talk about how you then can use the unique characteristics of water to automatically extract water from those SAR images and then overlap these or overlay these water information with other information such as road information or where the buildings are located to understand impacts of flooding events. So these modern SAR sensors today provide these data sets regularly. This is again an example from the Himalaya. You see a time series of every 12 days observations for this area of interest. And again, you see the development of surface water, and you can even visually already see how surface water expanded and changed throughout the flood season in this area. This is Bangladesh, and the impacts you're seeing here are related to the annual monsoon flooding events that typically start in May to June of the year and end in September, October. Here, another example of the benefits of SAR for water surface mapping. This is a side-by-side comparison of an optical time series, in this case, over the Brazilian rainforest. You see in the optical data set that heavy cloud cover on many days obstructs the water surface from view, while the SAR time series on the left gives you consistent access to the surfaces underneath the clouds. And you can see here, hopefully, in some areas, how water surfaces are expanding. If you see my laser pointer here, you see expanding water surfaces that happen as rain falls in this region. So this sort of shows you a little bit the benefit of SAR datasets for monitoring hazards related to rainfall and flooding. I want to briefly talk about the different flavors of radar that are available for your use. So similarly to the visual range, in the microwave spectrum, we tend to split up the spectrum into different subbands. In the visual range, you would call these colors. Blue, red, green are all different parts of the visual range electromagnetic spectrum. In the microwave, we use a bit more complicated nomenclature for these different subbands. We use letters such as X, C, S, L, and P to distinguish different subbands of the microwave spectrum from each other. So X-band is the shortest of these wavelengths that are typically used for Earth observation. These X-band satellites have wavelengths of about 3.5 or so centimeters. They provide very high resolution imaging, and they are mostly used for understanding things like urban developments and are also useful for very small scale features and changes on the land surface. For the purpose of flood monitoring and sort of also analysis of ecosystems, X-band sensors have very little penetration into vegetation. And so what this means for you, if you're interested in monitoring flooding, it means that these X-band datasets cannot see water under vegetation. So this is one limitation that's very similar to optical data. If you have trees obstructing the surface, you won't be able to map water under those trees using these X-band datasets. Going to longer and longer wavelengths, the next wavelength subgroup is C-band radars. C-band radars operate in the order of about 5.5 centimeters wavelength. They are sort of the workhorse of SAR. Many of the satellites that are in space right now operate at C-band. The reason why C-band was picked initially is that it is able to provide information about a lot of different things. So it's sort of it's good at a lot of things, but not really perfect for any one of them. It still provides decently high resolution. It provides a little bit more penetration into vegetation, but it's not really good yet for extensive vegetation characterization. And it doesn't really have quite enough penetration yet to reliably allow you to discover water under vegetations. So it's useful for a broad range of things, but it's not really optimal for any of them. So that's why it was picked sort of as a starting point to be able to support data for a really wide range of applications. Sentinel-1, one of the missions that you likely will be using, is operating at C-band. To longer wavelengths, we have then S-band at about 7.5 to 15 centimeter wavelength, L-band, which is focused roughly at about 25 centimeter wavelength, and then P-band in the order of about 60 centimeter wavelength on average. The ones that we'll talk about today more is L-band. L-band is really good to provide global medium resolution SAR data. The NISAR mission, which we discussed earlier, operates at L-band at 25 centimeters. It's really good for geophysical monitoring. It provides substantial penetration into vegetation cover, which gives you good sensitivity to biomass. So the penetration into the tree canopy allows you to characterize the tree canopy and estimate biomass and other vegetation parameters. And the penetration also means that now at L-band, we are much more capable of seeing water under vegetation, which is a topic that will come up a little bit later again in this presentation. So remember, today we'll talk mostly about C-band, about 5.5 centimeter wavelength, and L-band at about 25 centimeter wavelength. In addition to cloud penetration, radar also provides another capability that you don't get as easily from optical data. And the capability is the exploitation of polarization. Now, what polarization is the orientation of the oscillation of an electromagnetic wave. So if you think of electromagnetic signals, they are so-called transverse oscillating waves. Transverse oscillating waves means that their direction of oscillation, here shown as this up and down sinusoid, is orthogonal to the direction of propagation. So the electromagnetic wave would travel from the hand, in this case, to this wall on the other side. So propagation is from left to right. But the oscillation is up and down, which is orthogonal to the direction of propagation. This transverse nature of electromagnetic waves gives us the ability, or allows us to, for these signals, it matters in which plane the signal is oscillating. So the signal can oscillate up and down, like in this case, but it could also be oscillating left-right in a horizontal plane. And it turns out that signals with different oscillation planes, they interact with the surface differently and give us independent information about the surface. The plane of oscillation we call then polarization. So a signal that travels in a plane that oscillates vertically, so up and down, we call vertical polarized, and signals that travel in a plane that oscillates horizontally, we call horizontally polarized. And to show you an example that these different polarizations indeed lead to different imaging results, I'm showing you here some examples. What I'm showing you at the very left is in this case, a L-band data set acquired by the ALOS Pulsar mission. So it's a 25 centimeter L-band data set. The left shows you the signal in an HH polarization. The two H's here mean that we are transmitting a signal that is horizontally polarized, so where the oscillation happens in this horizontal plane, and we are receiving signals that were scattered back from the ground. We are receiving those signals also in that same polarization. So it's horizontal transmit and horizontal receive. These are those two H's. In the middle, you see a data set acquired over the same area, now in vertical polarization. So here we have transmitted a signal in sort of this up and down vertical oscillation and received signal in that same polarization. And if you compare those two data sets to each other, you can see some differences. you see that this area here, which ends up being a water surface, looks quite different in VV than it does in HH. So you see there is independent information provided here. Also on the sort of southern end of this data set, you see differences between the HH and the VV, with the HH having higher brightness in some parts of this forest structure, in this case, on the lower end of the data set. If you have polarization capability, you can do also funny things. You can record cross-polarized signals. Those are data sets where you transmit a signal in one polarization. For instance, you transmit, in this case, in horizontal polarization, but you're receiving energy scattered back in the opposite polarization. So we transmit horizontal and we receive vertically. This allows you to understand depolarization. So in this case, you're recording signals that were changed in their polarization, and we'll talk a little bit later here on the slide what causes depolarization and what this cross-polarized term tells you. And it comes actually here. So these polarized data sets allow you to distinguish different types of scatters on the surface. And what we can distinguish are these three different scattering types from each other. We can, for instance, map out so-called rough surface scatterers. These are these signals shown in blue. So if the signal from the radar travels down to the ground and then scatters off of a rough surface in this single scattering event mechanism, this is a rough surface scattering event. And we'll see that there's a polarization that is particularly sensitive to rough surface scattering. A second physical scattering process that SAR can distinguish is so-called double bounce scattering. This is shown here in this red color. Double bounce scattering happens, for instance, on tree stems. So if a signal travels down from the satellite, it may hit the ground, it may bounce forward from the ground, hit a second vertical structure, like in this case, a tree trunk, and from there it may reflect back to the satellite in this double bounce situation. So vertical structures such as tree trunks, but also potentially light poles and other similar features, they provide very strong double bounce scattering. Other features that are heavy in double bounce are urban environments. You can imagine a signal come down, hit the surface, bounce off the side of a building, and then come back to the satellite. So that's the second kind of scattering process that SAR can identify and distinguish. And we'll talk on the next slide which polarization is strong at mapping out double bounce features. The third scattering process is volume scattering. What this means is we have, again, a signal come in from the satellite, and then this signal penetrates into a scattering volume such as a tree canopy. In that volume, the signal may bounce many times from branch to leaf to branch to leaf and back. So there may be hundreds of bounces within that volume before the signal bounces eventually back to the satellite. These many bounces in a random volume, those are the main process that can cause depolarization, that can cause an incoming signal of a certain polarization to lose its polarization integrity. So we depolarize the signal, and the return signal may have equal amounts of horizontal and vertical polarization. And so these cross-polarized signals that we looked at on the previous slide, they are really good at detecting the degree of depolarization and really good at quantifying volume scattering. And volume scattering happens very heavily in tree crowns and vegetation covers. So data at multiple polarizations then allow you to discriminate these different scattering types. And this is the case because rough surface scattering tends to be particularly strong in vertical polarization. Double bounce scattering is particularly strong in horizontal polarization, and volume scattering is the main source for depolarization, shows up very heavily in these cross-polarized terms. So these terms where we transmit one polarization, for instance, horizontal, and receive the other polarization, such as vertical. So if you have all these polarizations available, you could look at ratios in power. If a pixel has higher power in VV than in HH, it is likely dominated by rough surface scattering. To show you what different surface types look like in SAR images, I want to show you this example. This is a very large SAR mosaic, actually acquired by a mission called SMAP. This is an L-band mission operating at about 25 centimeters. And this mosaic shows the Amazon rainforest basin. If you know the area, this rainforest basin contains lots of tree cover and vegetation cover. Those are shown in these sort of intermediary gray landscapes. It contains some water surfaces and also some inundated vegetation. So these dark features shown here, these are water surface features. Those areas look dark because of the following reason. SAR satellites turn out to be observing the planet always in a slightly side-looking manner. This has to do with the way SAR images are formed. The process of SAR image formation, which we won't discuss in this lecture, necessitates that the SAR satellites always look slightly to the side. So there's an angle here that's not zero, that describes the degree of side looking of a satellite. So the satellite looks to the side, it transmits energy to the ground. If this energy hits a very smooth surface, then the scattering happens in a forward angle. So the scattering happens in an optical scattering process, where the incoming signal is scattered away from the sensor in this sort of opposite direction from that smooth surface. So a very smooth surface, such as a water surface, will return very little signal back to the sensor, and therefore will look always quite dark in these SAR images. And this is a fact that we will exploit when we try to detect water in SAR data. If you add roughness to the surface, such in this area that's circled in yellow here, this is an agriculture site. So these are fields that are plowed and cultivated. The plowing adds surface structure to the surface and roughness to the surface. This roughness means that the scattering happens into a variety of different orientations, and the sum of the signal now comes back to our sensor. It turns out the rougher the surface, the more signal is scattered back to the satellite sensor, and SAR is really good at measuring surface roughness this way. We see other intermediary gray surfaces here. These are vegetation surfaces. So here signal comes down, it penetrates into the tree cover. There are many bounces that are happening here, and then signal comes back to the radar. How bright these vegetation patterns look depends on the amount of structure of the tree canopy. The more biomass, the more above ground structure the tree has, the higher the radar brightness becomes. This is really useful because we can look at the amount of scattering in radar over tree covers and can use that to understand the amount of biomass. The more scattering, the higher the biomass of the forest. Lastly, in this area, you see these very bright patches. Those are really interesting, and we'll get back to a little bit later. What's happening here is we have inundated vegetation. At L-band, we have the ability for the radar to penetrate through the tree cover enough to incur scattering on the surface. If that surface is a water surface, we have very strong forward scattering on this water surface, the forward scattered signal will then bounce off of tree stems in neighboring trees, and from there will be sent back to the radar. So we get a very strong double bounce effect that makes these inundated vegetation features very bright. And we'll see later that these very bright features in rainforests, in other vegetation covers, can be used to understand the amount of inundated vegetation in an area. So as mentioned, in order to be able to see the water under vegetation, we need to be able to penetrate through the vegetation. It turns out the amount of penetration is dependent on the radar wavelength. So the shorter the wavelength, the less penetration is available for the same type of target. So if we take a tree stand and we observe this tree stand at, say, 3 different wavelengths, such as X band, C band, and L band, you can see in the sketch here is that the longer the wavelength becomes, so we go from 3 centimeters at X band to 5 centimeters at C band, centimeters at L band, the higher the penetration into that vegetation cover becomes. So this means that L band is really useful for vegetation penetration and is much more useful for seeing water under the tree covers. This penetration ability also holds true for some dry soil areas like dry alluvium, the long rate. The same is true for glacier ice and snow cover. The longer the wavelength, the easier we can penetrate into ice and snow, and the deeper we can penetrate into these surfaces. This means a short wavelength, such as X band. These radars scatter mostly off of the tops of tree canopies. C band to L band has then increasing penetration ability, and longer wavelengths such as L band are useful for mapping of inundation under forest canopies. So upcoming missions such as L band will give you improved capability to map water not only in open terrain, but also find water under forest canopies. And an example of this you can see again on this slide. This is L-band data coming from a Japanese mission called ALOS-1. These data were acquired in around in the early 2000s. This is an area in Peru. And what you see here, you see the same area covered in 2 different times of the year. The left data set is acquired during the dry season, where the water under the vegetation is fairly limited. And on the right-hand side is a data set acquired during the wet season, where we have more water under vegetation. In both cases, you can see that there's some water present in both dates. This feature, for instance, is a water under vegetation feature that also survives during the dry season. But during the wet season, you can see that there's substantially more open water under the vegetation cover. You have water over here in these bright patches. You see a lot of water also in these brighter patches up here. So you could use this to map out inundated vegetation using these L-band data sets. So now we have an understanding roughly what drives radar scattering, and we already understand a little bit about how surface water looks in SAR images. I want to dig into these surface water signatures a little bit more so that you understand what to expect when flooding develops in your area of interest. So the way we can detect surface water signatures in SAR data has to do with the different kinds of scattering we observe on these very smooth water surfaces. So if you have a side-looking radar instrument and the signals travel down to the ground, if the signal hits a smooth water surface, it will incur so-called specular reflection. So the incoming energy will be scattered forward in the opposite direction. This means over water, we have very little scattering that comes back to the radar, and water typically looks quite dark in SAR images. You can see that here on the right-hand side. This is a data set in Norway, where you can see these very dark patches. Those are lakes in this landscape. In contrast, if the incoming signal hits regular land surfaces, such as bare soils or vegetated terrain, we incur diffuse scattering. This is because of the roughness of the surface and the structure that grows or is on top of the surface. Diffuse scattering means that the incoming energy is scattered into a variety of different directions, including the direction back to the radar. So regular land surfaces look significantly brighter than open water. And again, you can see that quite nicely here in this image on the right, where the water surfaces look distinctly darker than the regular land surface. And so we can then think about what the radar cross-section observed by a radar looks like as rain sets in and flooding occurs in a landscape. So I want to show you briefly three SAR signatures for three different types of landscapes. And so what you see in both cases, we have a situation where at the beginning of the time series, so time is shown here on the x-axis, we have a reasonably dry surface. So in this first observation spot, let's assume that rain is starting to fall. Early on in this time series, we have a relatively low soil moisture. And then as rain sets in, you see that progressively soil moisture is increasing. So this left panel here shows you the change of soil moisture over time as precipitation is falling. At some point in this time series, the surface may be completely fully saturated. And at this point, this is the point when surface water will form. So the soil is now not anymore able to absorb additional precipitation, and surface water and puddles on the surface are forming and expanding. So this is where you have flooding in the landscape. Now, what does this look conceptually in the SAR data set? As the soil moisture or the moisture of the ground increases, this leads actually to a continuous increase in the radar scattering of the surface. Soil moisture turns out to be a very strong driver of how strongly microwave signals interact with soils. The wetter the soil becomes, the more effective it scatters radar signals, and therefore the brighter the radar signal becomes. So initially, as the moisture content increases, we have a continuous increase in the radar cross-section of that soil in a time series. But then when surface water develops, we now have standing water. This standing smooth water surface causes the radar cross-section to drop into the basement here, because now we have specular reflection. All the incoming signal is scattered away from the radar, and we get very dark signals from this open land surface. So if water appears in open land areas, this is the radar cross-section time series you would expect. First brightening, and once floodwaters appear, you get very dark responses. This is in contrast to water forming under vegetation canopies. So in this case, we have trees on the landscape, and depending on your radar wavelength, you may be able to penetrate through these trees during both dry and flooded conditions. If there are dry conditions and the signal penetrates to the ground, you incur sort of diffuse scattering on the ground. So some of the scattering comes back to the radar, a little bit bounces forward against the trees, and then comes back to the radar. So we have moderate direct scattering and moderate double bounce scattering from these tree canopies. If we, however, add water to the surface, so we have now rainfall and surface water is forming, we get, first of all, much stronger scattering on the surface. If water scattering is forming, the scattering is a forward scattering case. So we have specular reflection with forward scattering. The forward scattered signal now hits the tree stem very effectively and comes back to the radar. So the scattering becomes much brighter in this area. So looking again at that same time series, so again, as rainfall develops, we have first a gradual increase of radar backscatter related to an increase of soil moisture. But now at the point when surface water is forming, the brightness actually becomes very bright. So you jump up instead of down because we get very strong double bounce signatures in under these vegetation canopies. So there's a difference between open land. In open land, the scattering went down to 0. In flooding under vegetation, the scattering jumps up to very bright double bounce scattering in inundated vegetation. So this inundated vegetation, again, as a reminder, is mostly observable at L-band, such missions such as NISAR, much more so than in currently available C-band datasets from Sentinel-1. To show you an example of flooded vegetation, you see here 2 cases of the Amazon rainforest actually in Brazil. On the left-hand side, you see a situation where there is no flooding under the trees. This is during the dry season. You see the field observation here on top. And on the bottom, you see the related SAR observation. What you see here is in black. This is a river going through the Amazon rainforest in this case. And around it, you see moderately gray value bright vegetation scattering in the area, scattering from the trees. At this L-band data set now, if we get into a flood season, now we have standing water under these trees. This leads to strongly enhanced double bounce scattering. And you can see that double bounce scattering very nicely in this data set. So all of these bright areas in this data set is inundated vegetation that you can easily map out, either in a GIS system or using some sort of an automatic technique. I'm going to skip forward real quick and show you a couple of examples of these scattering phenomena. So this, to show you what this looks like in reality, I'm showing you a time series of data sets over India. So this is the eastern part of India. Also here during the monsoon season, there are floodwaters that are forming. The river that you see go through these data sets is the Ganges River. And you see that during some time steps early in the season, the background looks more or less evenly bright. This is at the end of the dry season. And then as rainfall sets in during the monsoon, you see more and more dark patches show up that indicate surface water. Now we can pick a pixel in this data set. We're picking this pixel over here, indicated by this symbol in the map. And if we look at the time series for this pixel, you see a graph here shown on the left. You see we have an early phase where scattering is fairly stable at about a brightness of -5 decibels. And then the radar brightness gradually decreases and settles into a much lower radar brightness at about -20 dBs. And so if you want to interpret this, you can interpret this in the following way. This is the before flooding radar brightness here on the very left. And as rainfall sets in, more and more of this pixel becomes flooded and inundated with water. And at a certain point, this entire pixel is inundated, and you get much darker scattering from the specular reflection you get from the inundation. So you could not only identify this pixel as being flooded, but you could also roughly draw a line at which time step this pixel was completely inundated. To show you another example of this data point number 2 here, right next to the river, you see a little bit of a different behavior. You have first again around roughly about -5 dB stable scattering. as rain sets in, we then get actually an increase in brightness at first, and then a decrease in brightness later. And the phases that you see here is that as water next to this river is rising, we have vegetated terrain around that river. Initially, there's water happening under the vegetation in this area, which leads to a brightening of the radar cross-section that you see here. But at some point, as the water continues to rise, this vegetation in this area, which is not very tall, is actually completely inundated. And when it's completely inundated, you see how the radar cross-section then falls to the minus 20 dB indicative of surface water. So we have initial inundated vegetation, and then at some point completely submerged vegetation in these pixels. A third data set I show you over here. So these are wetlands that are slowly inundating in the time series at this point number 3. And here you see that we have again minus 5 dB background scattering early in the time series. Then about in June of that particular year, rain sets in and the radar cross section drops to a certain level of about roughly minus 10 dB. And then at a later stage in August of that same year, it drops even further to minus 20 dB. We already know that the minus 20 dB is the fully inundated, is indicative of full inundation of a particular pixel. But what happens in between is that this pixel, which has a 30 by 30 meter footprint, for a while was partially inundated. This can happen if there's topography in the landscape and you have mounds and valleys. The valleys will fill up with water first. So part of that 30 by 30 meter pixel has standing water, and other parts of that pixel are still elevated terrain. And only when also the rest of the pixel gets inundated, the radar brightness will fall to that minus 20 dB level. So these time series are really useful to understand how flood progresses and to pick time steps at which a certain pixel became fully inundated. Now at the very end, I want to show you how we can actually map these water surfaces using SAR. And it's all based on this idea that water surfaces look much darker because of that specular reflection that we've already discussed. So we're trying to exploit this darkness of surface water features to automatically identify them in images. And the way we do this is, or a very simple way of doing this, is using a thresholding technique. And so what we are counting on is that if we create histograms from SAR images, a histogram is basically a bar chart where for every brightness value, radar brightness value, we count the number of pixels that are characterized by this particular brightness value. So this black line here in the background is a histogram of one SAR image. What it shows you is that you have most pixels have a radar brightness roughly of about minus 5 dBs, somewhere between maybe minus 8 and maybe minus 2 dBs. Most pixels have radar brightnesses like that. These are pixels that predominantly belong to the class land. So these are rough surfaces and vegetation types that form regular land surfaces. You see there's a second order appearance of pixels. A lot of additional pixels have a radar brightness here in this case of about maybe minus 17 dBs. These pixels are significantly darker than the average land pixels, and those darker pixels belong all to the class water. So if you look at this histogram, you see this histogram has two distinct, if you want, humps. We call them usually two different modes. And the darker mode usually relates to water, and the brighter mode relates to land surfaces. And we can draw visually a line that separates pretty well the water pixels from the land pixels. So this is what a thresholding approach is doing. It tries to find a separating line, pixels that have brightnesses below that threshold value we would classify as water pixels, and pixels that have a brighter values than that threshold we would classify as land. And you can see visually that this threshold is pretty good at discriminating those two classes from each other. On the left-hand side, you see a second case. Again, you see a very distinct separation of water and land. Again, here we can draw a threshold line that separates water and land pretty well from each other. So what this slide shows you is, first of all, that thresholding is a really convenient and easy way to do water mapping in SAR images because it exploits this dark signature of water, but it also shows you a little bit of the complications of this technique. You see, first of all, that the water and land class are not equally separated in those two cases. These two cases are distinguished by some geometry characteristics. So one of them is acquired with a look angle of 23 degrees. So this is a radar that looks very steeply to the ground. The other one, the other radar looks a little bit more shallow. This observation has 45 degrees. The point here is that different observations may not provide you equal separation between water and land, and the optimal threshold that distinguishes water from land may also not be in the same case. So in the right-hand side case, you would draw a separation line roughly about -17 dB, while on the left-hand case, you would draw it at about -10 dB at a quite different brightness value. So a key to a successful approach is to automatically determine what is the best separation line between water and land, and we may have to pick that optimal threshold for every single scene, because for every single scene, the separation between water and land may be different. So we are looking for an adaptive approach that automatically finds the best separation threshold for every single data set. And so the approach that you will exercise in a lab is doing exactly that. It is performing an adaptive threshold-based surface water mapping. It is an approach that we developed in an applied science project, a very simple but quite robust threshold-based approach. This approach was actually used by a number of people, or similar types of thresholding approaches were used by a number of people. For instance, there's a paper that's listed here on this slide by Sandro Martinez et al. From the German Aerospace Center that published a very similar approach in their paper from 2015. Essentially, what we are doing is we take original SAR data sets, we do some pre-processing to these data sets, essentially to geocode the data sets and remove some image distortions that you get in SAR images. So this step number one prepares data sets, geocodes the data sets so that we can do flood mapping on these images. Once we have prepared the data sets, we can do the automatic thresholding. So most of the secret sauce of the approach is hidden in this step two, where we're trying to automatically find the best separating threshold between a class land, which is the brighter class in a SAR image, and the class water, which is the darker class in this particular SAR image. So step two provides the threshold determination. Based on this threshold, we can separate land from water classes, and we get what we often call an initial flood map or flood candidate map. We usually do a little bit of post-processing on that map, which is shown in steps 4 and 5. This post-processing is mostly to remove some false detections. Sometimes we may detect land pixels as water pixels. There may be reasons why sometimes certain land pixels are dark, even though they don't contain water. So in this step 4, we try to identify those pixels and remove them from the initial detection. And in step 5, in this approach, we also perform an additional step where we try to separate permanent water from actual floodwater extent. So permanent water would be the permanent extent of rivers, permanent extent of lakes, in contrast to additional water you get during a flood situation. In the lab exercise we'll do here in a sec, we will exercise steps 2 and 4 to get to an initial flood map and then a post-processed false alarm reduced flood map. Just briefly, how the original flood threshold detection works is, so we need to find a way of automatically finding the best classification threshold for a scene. And the way we do this is we take a SAR scene like this. This is a scene that has about a 250 by 250 kilometer footprint. And let's assume that our scene contains some water. So we have a lake and a river in that scene. What we do first, we split up the scene into smaller scenes. We call those tiles. These tiles are typically about 200 by 200 pixels in size. And of all of these tiles, we try to initially identify tiles that contain roughly about equal amounts of water and land in them. And the way we identify those tiles is we look for tiles that are darker than the average tile brightness, and where the distribution of brightnesses in a tile has a larger standard deviation than the average. So what does this mean? Tiles that have both water and land in it, they are darker than the average tile brightness because the water surfaces are much darker than the land surfaces. So those tiles are biased low in average brightness compared to a tile over here, which only contains land surfaces. So that's the first indicator. So this first step, by looking at average brightness, will detect all tiles that contain water. So for instance, this tile here marked in red, but also potentially this tile down here, which basically contains only water. To then focus on tiles that contain both water and land, we also look at the standard deviation. So we basically take all the pixels within the tile and calculate the brightness standard deviation. If we have both land and water classes in here, the standard deviation will be very large because we will have very dark and very bright pixels. And so the combination of average brightness and standard deviation lets us select these few tiles marked in red, which contain both water and land. And these are very ideal tiles to do threshold calculation. We can then, for each of these tiles, find a best separating threshold between the water mode and the land mode. We get, for instance, 5 such thresholds from this technique, and we then end up averaging those 5 thresholds to get a final threshold for a scene. I'm not going to go into too much detail into the post-processing, but once we have a first detection using this automatic thresholding approach, we can get some false detections. Those happen often in topographically inclined terrain where we may have radar shadow. It also happens sometimes in terrain that, say, may be covered in snow, such as higher elevation. You may have sometimes snow cover. During warmer days, the snow cover may melt on the surface. It may also look very dark, similar to a floodplain. And so those we may want to remove from our original detection. And our approach uses a set of criteria to identify pixels that are potentially false detections. We look at the radar brightness of those pixels. If the radar brightness is very close to our threshold, then we basically are saying we are not so sure about this particular detection. We also assume that flooding happens mostly in flat terrain. So if we have flood detections in areas where the surface slope is very steep, we also doubt a little bit that this is a correctly classified pixel. So we have a few of those rules that we put in place to clean up our original detections. And these rules work pretty well. To show you an example, these are flood detections in a very topographically inclined region in the Hindukush Himalaya. This is in the Himalaya mountains. And on the right-hand side, you see the SAR scene in this particular case. On the left-hand side, you see the original initial flood candidate pixels. Many of these flood candidates detected here are actually false alarms. These are pixels that happen to look dark but are not water covered. Once we apply the post-processing step, many of these pixels are removed. So you see here in the comparison, so this here is before post-processing. We see lots of false alarms. After post-processing, many of these false alarms are gone. And these features that are left here, actually, those are true water bodies. This, for instance, is a high altitude lake in the Himalaya mountains. So it's quite effective post-processing step. Also, this step is included in your little lab exercise. So this is a very simple but yet quite powerful approach to water mapping. On this slide, I show you that we actually built a service based on this technique to do continuous water mapping in the Hindukush Himalaya region. So we do water mapping for Bangladesh, northern India, southern Nepal, and southern Bhutan. This slide includes a link. So once you have these slides, I encourage you to look at this link and explore that platform that we've built that automatically does water mapping in this region. In this platform, we provide two layers. One of them is the inundation information in sort of a lighter blue color, and in a darker blue color, we also provide permanent water extent to allow people to distinguish between the floodplain and the perennial water surfaces in the landscape. And because we have data sets every 12 days, you can animate this information in this web service to sort of monitor how the flood situation is developing in that particular region. This shows you a time series animation of flooding in Bangladesh from 2021. Where you can see how the floodplain is continuously expanding during the early phases of the monsoon in that particular year. Here an example how this information can be used. This is an example where you see on the left-hand side the surface water, on the right-hand side, the surface water extent extracted from our service. This is for the northeastern part of Bangladesh. And on the right-hand side, on the left-hand side, you see an aerial photo to give you an impression of what that water extent looks like on the ground. Again, because you have data sets every 12 days, you can not only map water extent once, you can map water extent regularly. And this data set shows you, or this slide shows you how you can use multiple data sets to do additional analysis. On the left-hand side, you see a surface water extent that's analyzed as a function of time. So for every time step here, you see the amount of surface water that's present in the scene. This is for 2020 in 3 provinces of Bangladesh. And you can see that in this particular year and this particular area, floodings commenced in about early May of 2020, initially encouraged by Cyclone Amphan, which was a strong cyclone that hit Bangladesh a bit before the regular monsoon start. So there was early surface water extent, and then in June, the regular monsoon kicked in and added additional water surface to this area. Water extent peaked in early August and then slowly receded until the end of the year. So that's one way of how you can analyze these data sets. You can also, if you have multiple observations, you can calculate how many days particular areas are inundated. So this is a heat map here that shows you sort of reddish regions are inundated for many, many days, and blue regions are inundated only for short periods of time. This information can be useful if you have agriculture areas and you want to understand whether the crops in the area may have survived or may have drowned during an inundation event. We've done a great deal of evaluation of this workflow too to understand the performance of this. I want to just show you a brief flavor of this analysis. We have here a comparison between our water detections coming from SAR, in this case from Sentinel-1 SAR, to water detections from optical satellites. There are established methods how you can detect water from optical data as well. And if you happen to have cloud-free optical data, we can try to find pairs of cloud-free optical and SAR data sets that are within 1 or 2 days time difference to each other, and then compare these water maps to each other. And this slide shows you some examples. So on the very left, you see SAR data sets, water extent derived from SAR. In the middle pane, you see water extent derived from optical data at time steps reasonably close to the SAR acquisitions. And on the right-hand side, you see the difference. So everything's in blue on the right-hand side, shows equal water extent, and little patches that show red and light blue. Those are differences between the optical and the SAR detections. But you should see in this animation that SAR is quite good at monitoring an event and seeing the changes of water extent equal to what you would get from optical data if you were lucky and optical data were, and you get enough cloud-free optical data sets. So before I go into the lab, I want to briefly talk about limitations. The limitations for these threshold-based mapping approaches, one of the main ones has to do with wind roughening on water. So the premise of the approach was that water surfaces look very dark. And if you remember, the reason why they look dark is because water surfaces tend to be very smooth. This premise is violated if we have strong winds during a SAR acquisition. So if you blow wind over a water surface, you create small ripples on the water surface. Those are called capillary waves. You can see that in that little image on the left-hand side. And this causes some roughening of the surface and an increase in brightness. So during days of very strong winds, this threshold-based approach may run into some limitations. You can try to mitigate this problem by doing thresholding not only on the VV polarization, on the co-polarization, but also on the cross-polarization. It turns out these cross-polarizations are more resilient to water roughening. So there's some workarounds to mitigate the wind impact. In the notebook, the exercise that you'll be running will actually use both polarizations of Sentinel-1 to be more robust to wind impacts. Another main limitation is water under vegetation. Only certain radars will allow you to see water under vegetation. This is particularly true for the longer wavelengths such as NISAR, and much less true for the shorter wavelengths such as those provided by Sentinel-1. So the data that you'll be using in your exercise, those are Sentinel-1 data sets. Sentinel-1 is great at detecting open water surfaces, but not as good at detecting water under vegetation. A third one that I want to make you aware of is SAR, because of its side-looking nature, has some limitations of seeing water in dense urban environments. The reason is if you look sideways to the ground, you may get large shadow effects where there's an area behind tall buildings that you cannot see with these side-looking radars. So everything that you see here, where I'm marking my mouse, this area where my mouse is at, this area cannot be seen by the radar because it gets shadowed off by this tall building here in the front. So shadow effects provide some limitations of seeing surface water in urban settings. That's also something to be aware of. And so here is an example of this impact of vegetation on water detections. This is, in this case, data sets from Sentinel-1. So these are C-band data sets The two shades of blue here are water detections, surface water that was found in those Sentinel-1 data sets. And what you may see is that the water detections end at the edge to this sort of light green region. This light green region is our mangrove forests. And it turns out that the radar signal cannot penetrate through those mangrove forests. So even though there is likely water under those mangrove trees, we cannot detect this water using Sentinel-1, using the C-band Sentinel-1 dataset. L-band datasets from SAR will have much better capability to also detect water under these trees. Again, L-band is the way to go if you're interested in detecting water under vegetation covers. So with this, I want to end. I want to give you at the very end a homework assignment. We have a little exercise that is created in a so-called Jupyter Notebook. I'm going to spend 5 to 10 minutes real quick to explain to you how to run this Jupyter Notebook and what kind of data sets you will see in this particular Jupyter Notebook, and then would send you off to perform this exercise on your own time. So the link to the notebook that we'll be using is in the slide deck. And so on this slide here with the lab exercise, you can click that link. What this link is doing, it is opening a Jupyter Notebook for you. And I will explain to you how to run through this exercise real quick and how to use these Jupyter Notebooks. So now you see that the Jupyter Hub is spinning up. The environment was built and your environment is now spinning up. And so the exercise that you'll be walking through is conceived as a Jupyter Notebook. So what I'm explaining to you real quick is what this exercise is doing, what you will be working on, and how to use Jupyter Notebooks to exercise this particular homework assignment. So Jupyter Notebooks are ways of sharing executable workflows with users. And so in this particular workflow is doing flood mapping using the thresholding algorithm we just talked about on a stack of Sentinel-1 SAR images. These notebooks are composed of sets of individual cells that have to be run in order. You can see here the outline of one of these cells. So the this blue line indicates the outline of that first cell that we have to run through. This first one is a so-called markdown cell. You can see what cell this is also on the top row of this interface, where you can see here that this is labeled as a markdown cell. Markdown cells contain text and instructions that explain to a user what the notebook is doing. This next cell is also a markdown cell. It tells you a little bit about how to run this particular binder environment. A second type of cell that we're using in these notebooks are so-called code cells. These can be identified with the gray background. Code cells then include executable code. They have to be run in the order as they are given in order to exercise this notebook start to finish. So this notebook is walking you through that flood mapping workflow as shown in the slides earlier. So this graphic you saw earlier, and the notebook includes the preparation of the data, the initial adaptive threshold calculation, the creation of an initial flood candidate map, and then some post-processing procedures to clean up those masks. So in order to execute those code cells, you have to click into one of these code cells and then run the code cell. You can do that by clicking that run button, which is sort of this sideways triangle here. So you can click on that and it runs the notebook. You see that the notebook is running because there is a little star in between these square brackets. Once the code in that cell was completed, that star is being replaced by a number. This is a sequential number that sort of reminds you which code cell you have already run and which one was the last one you've run. So you can run through these code cells now one by one to execute these functions. It is explained in a notebook when you walk through it what these functions do. So we initially run through a set of predefined functions that we will use later in the flood mapping procedure before we then end up grabbing the data set. So I'm just going to run through these code cells one by one to show you what kind of end result you would expect once you ran through the notebook all the way. So let me run those, and then I go back and explain real quick. So these early code cells here load the data set. We are using a stack of Sentinel-1 images near the city of Malda. This is near the Indian-Bangladesh border. We have data sets that span the early part of the 2020 monsoon season. We have a total set, I think, of 15 or 16 data sets that we're analyzing here. These early code cells are downloading those data sets. This is a prepared data stack. You see here all the different images that we are analyzing. These are GeoTIFF images. The file names here show you the dates of that image. So this is from the 2020, from June 24th of 2020. And for each date, we have two data sets. We have the VV, the vertical transmit, vertical receive data set, and the VH, the vertical transmit and horizontal receive data set. So we use both polarizations for robust flood mapping, especially to be robust against wind impacts, as we had discussed earlier. So we load these data sets in. We are also using some ancillary information in the form of height above a nearest drainage layer. This is used to improve thresholding and post-processing. I didn't talk about that to a great deal in the lecture, but it's you can find some information in this notebook to explain how this hand layer is used. And then there's a longer code cell that does the initial flood mapping. So this calculates the adaptive dynamic thresholds for every scene to create initial flood extent maps. So this is a lengthy code cell that encodes all of the processing. And if you run that code cell, it's going to go through all of the images. So we have 16 data sets. For each of the 16 timestamps, we have two images, the VV and the VH image, that are both being thresholded to calculate flood extent. So it goes through all of these images, calculates adaptive thresholds. These thresholds are shown here, what the numbers of these are. You can see that every image gets a different automatically determined optimal threshold to separate the water and land features from each other. Once done, there is a code cell that lets you evaluate the flood mapping results. So here we've analyzed the 16 time-step time series, where you see that early in the season, the surface water extent was fairly small. It mostly was composed of the permanent water bodies in the landscape. And then as rain set in, here in this case in June of 2020, you see a continuous increase of surface water extent until early August, before a water extent then slowly recedes. Also shown in this plot is a sort of red dashed line is the average flood area extent throughout this time series. Later on in the time steps, there is a way for you to visualize the water detections on top of the SAR image. So this shows you an example of these water detections, and you can visually understand the fidelity of the detections. This is an interactive plot, so you can actually go in, and with that little button here, you can draw up a zoom window to sort of zoom into an area of interest and analyze the flood detections with a little more detail. So once this zooms in, here you can see in more detail the pixels that were labeled as surface water in the landscape, which in this case are all the dark pixels, and the land pixels are still marked as land or not water pixels in this case. And at the very end, it also creates a summary statistic. We talked about this in the slide deck. One way of utilizing time series of water detections is you can analyze for how many days specific areas were inundated. So in this time series, you can see the dark red pixels were inundated throughout the time series. We are covering here 45 days. And you see that's, of course, the river, which is permanent water. And then we have some features also in the floodplain that were inundated for more than 30 days during this flooding event. So please have fun with this notebook. Again, ensure that you exercise all of these code cells one by one in sequence, and you do that by clicking into the code cell and then clicking that little sideways run button to run one notebook cell. Once this one's run, please go to the next code cell and execute the following one to successfully run this notebook start to finish. In this notebook, there are a few stopping points in these green boxes where you can contemplate the questions that are posed to you in these little green boxes. And please follow these instructions to get a bit better feeling for the quality of the water mapping that is provided using this particular approach. I hope you have fun with the notebook and will be able to exercise this completely on your own time.
Thank you very much for that amazing presentation and demonstration. So to summarize the key points from the presentation, globally and regularly acquired data from Center1 and NISAR are excellent for hazard monitoring applications. SAR has excellent abilities to map surface water in all weather conditions. Threshold algorithms are able to provide automatic water mapping capabilities. L-band provides improved ability to map water under vegetation. So it's a better band than C-band. And finally, there are several public water mapping services that take advantage of the capabilities of SAR. And Dr. Meyer would like to acknowledge Copernicus, the European Space Agency, and the NASA Alaska Satellite Facility DAC for access to the Sentinel-1 SAR data. Thanks to NASA Surveyor for funding the HydroSAR development efforts, and a special thanks to Thomas Meyer and Lori Schultz and others for their contributions. And here is Dr. Meyer's contact information, his email address, if you would wish to contact him about any questions related to the material that he presented today. And for those wishing to dive in a little deeper, here's some relevant literature that will provide more information and further details about using SAR for detecting and monitoring floods. And finally, before we end, here are some links that might be of interest, and they are to selected existing and upcoming SAR-based water mapping services. So with that, we conclude this third and last session of this webinar series. A very big thank you to Dr. Franz Meyer for the presentation and demonstration. Thank you to all participants for the questions that are coming in and for your participation and excitement in this topic. We will now start the Q&A session. Great. So we've been assembling your questions in a Google Doc, and we will share our screen here shortly. And we'll work our way down. Dr. Meyer has started answering your questions. So what I'll do is I'll read the question and he can then provide the answer. We'll work our way from the top down. Before we start, just wanted to remind you that the homework is already posted online, and that the recording and the presentation and the transcript for this Q&A document will also be posted online. Okay, so welcome, Dr. Meyer. Let's start with the first question. How can temporal coverage be selectively higher in certain parts of the globe, in Europe 6 days and 12 days elsewhere? I was thinking it would be somewhat the same.
Yes, do you want me to answer verbally? Yes.
Yes, please go ahead.
Yeah, so as mentioned here, the constellation itself, in principle, with the 2 satellite constellation, could observe 6-day sampling everywhere. However, limitations occur in terms of data rates, so how much data can be downlinked through the available downlink stations, as well as through the duty cycle of each satellite. So each satellite can only be on for a fraction of the total orbit. And so Sentinel-1 with these limitations isn't capable of observing everywhere globally every 6 days. So they focus on places that funded the mission. It's a European funded mission, so they ensure 6-day sampling over European grounds. They also have requirements over the Arctic Ocean to help in the monitoring of sea routes. And so also there where they have 6 days or better coverage. And they provide additional 6-day coverage over hazard regions, many of the geophysically active regions, such as volcanic and earthquake sites, also receive pretty good 6-day sampling. California is one of those. Hawaii is another one of those. I hope that answers the question.
Great, yes. Thank you very much. Question number 2, what is the most appropriate way to choose a threshold value for flood detection from SAR data?
Yeah, hopefully that was answered in the presentation. So in the end, it's best to adaptively choose a threshold for every scene because how dark water will look in a scene and how bright the land will look is a little bit different depending on acquisition geometry and environmental conditions. Hopefully that was conveyed in the presentation that approaches such as HydroSAR and similar approaches, they end up using an automatic way to always identify the best threshold for every scene.
Wonderful. Question 3, is it good practice to use SAR flood maps for validation of flood maps from other hydraulic flood inundation models?
Yeah, so these SAR-based flood maps have been used in conjunction with modeling actually in 2 ways. Some models use them for validation. That works particularly well in places where you have open surface water. Through the presentation, you've heard that SAR, especially at C-band, has limitations of seeing water under vegetation. So as long as you have open surface water, you should be able to cross-compare SAR and modeling outputs for cross-validation. Another way how SAR data have been used for some of these flood forecasting tools also is that they've been used as input data. So these days we are in the sort of era of deep learning and machine learning. And so a lot of these flood forecasting models have also ingested SAR data as sort of input to be better at forecasting data into the future.
Okay, question number 4. Can radar also detect sedimentation change under the water, that is, under the ocean or rivers?
Yeah, unfortunately, SAR, the wavelengths of SAR that are used for SAR, they are not able to penetrate into water surfaces. The dielectric change at the water surface is too high, and we are bouncing off of the surface itself. So we cannot see things like the properties of sediments on the seafloor. We also cannot see sort of sediments in the water column itself. So LiDAR data, some optical data sets are better here. There is some work that's been done to analyze surface structures such as wind roughening. I think there are questions later about that. Also the presence of like oil slicks on the surface, those have been analyzed with SAR. And in coastal zones, some folks have been using SAR to estimate shallow bathymetry. We can do that because there's a linkage between bathymetry and what wave patterns look like on the water surface. So we can measure wave patterns and then infer bathymetry from that. We can't measure bathymetry directly, but we can sometimes in shallow environments infer bathymetry from what it does to wave patterns on the surface.
Great. And for those interested, we have an ARSET SAR training to detect oil slicks, and that was the last ARSET training. I believe that was in 2022 for those interested in that specific topic. So question number 5, what is the expected real-time latency for NISAR and Sentinel-1?
Yeah, so Sentinel-1 has a fairly low latency. Usually you get fully processed data within hours, I would say, at max 8 hours after image acquisition. So it's great for a lot of monitoring applications. NISAR will provide data at about the same latency also for areas labeled as sort of urgent response. So these are, ongoing events that triggered an urgent response mode for NISAR. Also for those, you will get data at about the same latency. For most other data, the data will take a little bit longer, approximately a day, 1 to 2 days. This is because NISAR wants to wait for the final orbit solutions to be available so that we have the highest quality data available for analysis. But again, for data sets labeled as urgent response because they're affected by hazards, you will get data at about a similar latency as Sentinel-1.
Okay, question 6, where can I learn more about SAR? Are there any short courses or training related to this or a manual?
Yeah, so I've provided, there's actually lots of resources. It's been fantastic. The community as a whole has really come together and provided training resources for new folks to SAR through a variety of resources. I listed some of them here. I can expand on those too. And Erika, please chime in too. You have a really good overview of over the many trainings that ARSET has been doing. So ARSET has a number of trainings available for the theory of SAR, which is the one I listed here, but also for many applications. We have provided some resources too, those are listed here. I can work on those a little bit more. The last link I provided here to that Learn SAR website actually has a bunch of additional links to resources in it, such as the SAR handbook, such as some European resources and so on.
Wonderful. Yes, there are a number of different resources out there for different levels too. So
Yes.
we'll expand on this. Okay, question 7. Is it advisable to use the L-band data for flood monitoring in a densely vegetated area? And what is the resolution and how do you get the data?
Yes, so L-band data is going to be very, very useful for monitoring flooding on the vegetation. It's going to be particularly useful for many of the sort of South American countries that are suffering from flooding. The data from NISAR is a good resource for that. If you are in South America, you may have access now, I didn't mention that, to data from SAOCOM. And so if you put a note in there, I can find a link to SAOCOM resources. So NISAR will be available at sort of the 5-ish meter spatial resolution through ASF. Earlier in the lectures, you saw a link to ASF search interface, and through that you will be having access to NISAR data.
Great. Question number 9, is SAR... question 8, which band would be most optimal for mapping rice paddy fields?
Yeah, so I'm not an expert in rice mapping. I know there is an actual really good ARSET training that's linked below that focuses particularly on crop mapping. There have been work on both SAR and C-band and X-band SAR for mapping rice paddies and also the development of rice crops in rice paddies. Both of them were successful. So there's a variety of work out there. I'm not sure if we know enough quite yet about what's optimal for monitoring rice. But as more C-band, L-band, and X-band data become available, I think this is going to become more established.
Okay, question 9. Is SAR L-band able to penetrate highly dense and tall trees such as those found in tropical areas like in Ecuador or Colombia in order to create reliable INSAR and GRD products, or would P-band be advised in such cases?
Yeah, so L-band does have pretty good vegetation penetration capabilities, and it will provide better ability to track surface displacement using INSAR in places that are vegetated. So I would advise to initially work with L-band data, such as the ones that will become available with NISAR and the ones you may already have access to with SAOCOM if you're from the region. There is going to be so you'll enter a space where you will have L-band and P-band data available at the same time over those regions, Ecuador and Colombia. And it would be worth contrasting those two for their respective capabilities. You may have some very dense forests where L-band is not enough and doesn't provide quite the penetration you want, and you may have to pivot to P-band. But luckily, starting, I would say, 2025, so it's not quite there yet, but you're getting there. You will have data from both at both frequencies, and the data sets will all be freely available from both L-band and P-band, so that you can explore, what is the better band for your particular region. And I provided links to the missions here, and L-band data again will be available through ASF. P-band data will be available through ESA.
Yeah, so the next couple of years will definitely be exciting times in terms of new radar data becoming available in these different frequencies. Question 10. My request for an account in Open Science Lab is pending. Is there any other way I could access the data? And in part 2, in session 2 yesterday, some participants had questions about how long it takes for their ASF account to be approved.
Yeah, let's start with data access first, which is the second part of my answer. If you're just looking to discover data and download them to your local machine, you can always stop by our search client. The link is provided here, the search.asf.alaska.edu. If you actually want to do your research next to the archive, then Open SAR Lab is your way to go. We used to have a automatic open enrollment on Open SAR Lab until recently. Unfortunately, we had a few people enroll in the platform that abused the platform for things it wasn't intended for. So we had to at least temporarily suspend the open enrollment. So right now we're doing manual enrollment, which takes a bit longer, but you should get a response from the team within 1 or 2 days after your request. So I apologize for that and ask for your patience. But if you're requested for access, you should get an email from the team with information. We are working currently how we can accelerate the approval process while ensuring that the platform remains safe. So sorry about that. We only had a few cases so far, so most of the community has acted responsibly. But unfortunately, we had a few cases that prevent us for now from just granting you automatic access when you apply. So right now, it's going to take about a day or two until the team gets to your particular request. So I ask for your patience for that.
Okay, question 11. What is the difference between SHV and SVH?
Yeah, so the S in this case just stands for the backscattered power, and the HV and VH correspond to the horizontal transmit, vertical receive versus vertical transmit, horizontal receive cross-pole channels. It turns out while we formally do tend to distinguish between those two, for the spaceborne radars we have in space right now, those are the same. So whether you are acquiring in VH or HV, the response is intrinsically the same. What we usually do if we have both available, we average them to get a better signal to noise. But you can consider them identical if they're coming from the same sensor. So if you have VH and HV from Sentinel-1 or from, say, RadarSat or from a mission like that, you can treat them as identical for your research purposes.
Great. So let's jump to question number 13, since 12 is more relevant to session number 2. And in the interest of time here, question 13, I'm experiencing dark pixels in areas surrounding the river in the before flood image and bright pixels in the after flood image. Moreover, some researchers use pre-processing even in level 1 GRD2. Why is that?
Yeah, so we usually do pre-processing beyond what the GRD provides. We usually do a full geocoding and radiometric terrain correction. The geocoding makes sure that every pixel in your image does align with its correct physical coordinates on the ground, so that you can overlay optical data with SAR data sets. That's not always true for GRD data, especially in places that are more mountainous. So I suggest to do full geocoding. If you're working in GAE, the GE data are fully geocoded. What we also do is we often do radiometric terrain correction, which ensures that in every pixel, the radar brightness has physical meaning. So that makes flood mapping, but also other classification efforts more robust. So I suggest to do both RTC processing and full geocoding for your data sets. ASF has resources for those available. If you have questions, you can send me an email. There's also Opera, missions like Opera, they're providing now fully geocoded data for Sentinel-1 also. So follow up with me with my contact information if you have more information about that. Regarding the case of brightening after floods, it could be that you have vegetation, either taller grasses or maybe taller vegetation around the river that got inundated and caused a brightening in these areas because of increased double bounce there.
Okay, question 14. Could stormy sections of oceans be confused with land cover due to the scattering from the rough surface?
Yes, I addressed that at the very end. So wind blowing over water does increase radar brightness and makes sometimes water surfaces look like land surfaces in sort of their brightness characteristics. We do something to mitigate this problem by using both the copole, so the VV or HH band, and the crosspole bands, so the VH or HV bands together for flood mapping. The crosspole bands tend to be less sensitive to wind roughening and provide a bit more robustness. That being said, if you image during extreme wind conditions, say if you image during landfall of a hurricane or typhoon, then even the HV band may not be robust enough and you may lose some water detections because of wind roughening. So there are cases during very strong winds where you may have issues finding water using these threshold approaches.
Great. I'm going to jump to the more relevant questions related to this session and also those related to the demo. So let's just go to question 16. While doing sampling and classification, if we're certain about the local area that inundation occurred, but the SAR is not showing it, what do we do? Do we follow local observations or do we rely on what SAR is showing?
Yeah, so I would rely, if you're certain about your local observations, I would rely on those. You may miss water detections in SAR for a number of reasons. One of them is vegetation cover. So if flooding occurs under vegetation. The other one could also be mixed pixels. So if you have a SAR product that's provided, say, a 10 or 20 meter resolution, and the pixel is only partly covered in water, it may not be detected as an open water pixel because its brightness is a little bit elevated because the brightness is going to be a mix of the water fraction and the land fraction. And then lastly, what I also mentioned is SAR data is only available on certain days, and you may actually miss the peak of flooding. And so that may also cause a difference between the SAR detections and your local observations, is that if they come at different times and the event is dynamic, you may get a difference between those two. And in that case, if you're certain about your local observations, I would rely on those.
Okay, question number 18. This is related to the demo. Can we have a GitHub link for the homework notebook from the Hydro 30 via binder? I can't download the notebook.
Right, the notebook is exposed on GitHub, so you can download the notebook from there. I provided the link here in this document for you to go to and download the notebook file.
Wonderful. Question 19, you said flooding between trees becomes bright pixels. How about flooding in a residential area?
Yeah, so in residential areas, you may see a similar situation if the buildings are close enough so that you get a double bounce from the inundated landscape and the buildings around it. That being said, is flood mapping in urban environments with SAR is still a research topic. And there's a variety of different approaches out there to try to optimize flood mapping in urban settings. And a simple threshold approach like the one that we've shown today may not be necessarily your best choice. If that's something that you're most interested in, you can email me and I can provide you some links to literature.
Okay, question 20. Does soil moisture scattering used for flood detection behave similarly in slopes? In other words, could the same principle be used to monitor soil saturation on slopes?
Yeah, so SAR, one of the applications, NISAR actually will provide a global soil moisture product that uses this relationship of soil moisture to radar brightness. So in principle, yes, those principles also apply on slopes. If you want to know more about how to estimate soil moisture from SAR data, you can contact me and I can connect you with an expert. I'm personally not using SAR for soil moisture estimation, but I can connect you with some of the folks from the NISAR team that are working on the soil moisture product.
Okay, question 21. On slide 41, I've seen a white and bright line on the SAR images. What is that?
Yeah, so I should have mentioned that. In the example I showed on slide 41 is I used Sentinel-1 GRD images as a basis to provide sort of this time series. GRD images do not overlap between neighboring frames. And in fact, sometimes there are slight, very narrow gaps between two neighboring GRD images. And that's what you see here. So this line is a gap between two data sets. If you want to avoid those gaps, I recommend that you use Sentinel-1 SLCs, single look complex images, as your source for mapping. They actually slightly overlap with each other and ensure that you have contiguous mapping everywhere.
Okay, so we're at the top of the hour here. Let's just take two more questions and then we'll close off the session. All questions will be answered and posted on this Google Doc online. So let's just go to the next question. I'm not familiar, question 22. I'm not familiar with MyBinder. Is it like Google Colab?
Yeah, MyBinder is a free service that you can use to exercise a notebook. In that sense, it's similar to what Colab provides. It provides sort of temporal cloud computing as well as some temporal storage space. You need to sort of exercise a notebook and get familiar with the workflows in a notebook. It does not provide persistent storage, though. So if you want to do research, you may want to instead use something like Open Science Lab where you have more perpetual storage available. But yeah, so in many ways, it's similar to Colab. One difference is you don't actually need an account for MyBinder. You can just click the link and have it spin up. It will shut down after like 10 minutes and free the resource again. So it doesn't provide accounts, but it doesn't provide temporal permanent storage. So it's more to exercise a workflow and not to actually do your own research more consistently.
Okay, great. And then I'm going to jump as a last question. I think this is a really interesting one. It says, question 38, for optimal results with the algorithm, what would be the minimum length of the time series recommended?
Yeah, so this particular algorithm that we are using here, or I presented here, works on single images. So it doesn't actually require a time series. That choice was made intentionally so that the algorithm can be applied in sort of immediate response, where you may not have a time series available for your work. There are time series approaches too that use sort of change detection in time series to have more robust detection of flood extent. But the approach that we looked at here is a single image approach. However, of course, if you want to monitor the unfolding of an event, it makes sense to not only use a single image, but apply the approach to a series of images and then analyze the flood extent as a time series.
Wonderful. So unfortunately, due to time limitations, we can't get to all of these questions. Again, all of them will be answered. They've been collected in this document and we'll be posting the document in a couple of days. So with that, this ends this webinar series. I would like to remind everyone that the homework is online. Due date is November 17th. And you will receive a certificate of completion if you complete the homework by the due date and you've attended all live sessions. Before I close, I'd like to thank the ARSET team for making this possible. Brock Blevins, Selwyn Hudson-Odoi, Natasha Johnson-Griffin, Sarah Kutshaw, Jonathan O'Brien, Amita Mehta, Sean McCartney. And I would like to thank our amazing guest lecturers, Malene Johansen from the Arctic University of Norway, Erik Fueling from JPL, and today's amazing guest lecturer, Dr. Franz Meyer from the ASF DAC and University of Alaska Fairbanks. Before I close, Dr. Meyer, would you like to say any closing words?
I just want to thank you. I'm really excited for the level of interest that exists right now in the topic of SAR. If you have questions about resources, if you have ideas for how we can make these data sets more accessible, please reach out either to Erika, to myself, to ARSET, to ASF. We as a community, I think we want to make sure that these data sets that are becoming available are as useful to all of you as they can be, and we have still a long way to go. So your feedback and your input is very important for us, and hopefully we'll see each other at AGU or some upcoming conferences. If so, then please say hi.
Thank you very much. It's been a luxury having you here, Dr. Meyer, and we hope that you return and you come back, especially once NISAR is in orbit and starts generating amazing data. So we hope to have another ARSET training sometime in June, July, August of next year. Thank you so much to all of the participants. It's really refreshing to see so much excitement for SAR and a growing community of SAR users. As mentioned, any questions, please feel free to reach out to me, to reach out to Dr. Meyer. And we hope to see you in the next ARSET training or at any of the upcoming conferences. Wishing you all a great day, and until next time, goodbye.